Okay, good morning, everyone. It's my pleasure to present our result here. First of all, I'd like to thank the organizer, Professor Ren and Professor Bao, for extending the invitation. So today I want to review some of our work on the complex two-phase flow modeling. So we have the motivation that we want this to be applicable for petroleum engineering applications. And in many of these applications, we actually need to track multiple components. The reason is because we need to model this what we call partial miscibility. So normally, like from previous talk, you say we have many models, like Convex is one of this popular model, but that model is used for incompressible and fully immiscible two-phase flow. Immiscibility is for simplicity only, but in reality, many two-phase example actually have a certain miscibility somehow, some more or less. For example, even like air and water phase typically is assumed as fully immiscible, but we know that air component can somehow dissolve in water phase. Otherwise, all this fish will be die because of the lack of oxygen. So whenever you want to model the partial miscibility, then most likely you need to use the equation of state to model in order to calculate the solubility of the component into each phase. So that makes everything, the whole framework change. I mean, the good news is now that once you incorporate a realistic equation of states, you can make the whole system thermodynamically consistent. That's also good somehow in terms of design good numerical algorithm, because now you don't have to face a certain inconsistency in original, for example, the Kahinian model equation approach. So the plan, I'll first introduce some background information and motivation why we're going to do this two-phase flow with partial miscibility. Then we're going to show some results. So my focus is doing the petroleum engineering application with a two-phase or multi-phase system. So we have actually a wide collection of different scales in terms of modeling efforts. For the largest scale is what we call Darcy scale. That's a scale that people actually develop commercial software to for predict what's happening in a petroleum reservoir. So we have many models like single-phase, compositional, multi-phase. There's many different numbers. But those models require permeability, say capillary pressure function, and many parameters that depends on pore scale. So pore scale is what is all relevant to, I think, to this workshop. So it's based on, so it's like a free flow inside of the rock of each pore, and you're trying to model two-phase flow. If you assume it's incompressible, immiscible, then you can use Kahinian Navier-Stokes equations. So that's one of the popular approach people are using. It's quite mature now in recent decades. But there were also other approaches. So we are trying now looking at the equation-based diffuse interface model. So that you can view this like an extension of Navier-Stokes Kahinian. So for the momentum transfer equation is still Navier-Stokes, but we use a component transfer equation to model each species. So that's the kind of extension of Kahinian equation. So the framework will be allow possibly compressibility and partial miscibility as well. And of course, when you can also study this thing in a molecular level, which can also give us some idea about what's going on. And we also have some effort on this. And this can also give us some parameter to fit in this model over here. So the Kahinian Navier-Stokes equation model have many forms. One of the forms look like this. So this can be very useful to study the two-phase, like oil and water system, two-phase flow inside of a rock to telling us a lot of things. That's why we was very interested in things. For example, that if we want to study the effective wettability to two-phase flow inside of a porous media, then you can study a single channel, and you can say a oil droplet touching the oil. You can change the wettability and the flood of water to see what's the difference. So that could be one case. So this can be solved by Kahini and Navier-Stokes. And you can, if you have a roughness on the oil, on the wall of the channel, and you can also study by changing different parameters, for example, the surface roughness, and to study what the trapping of the oil phase. So suppose the oil phase is a blue one, so under certain wettability and roughness is a certain trapping, and that's what we're interested in for petroleum application. So this is what, in the data scale, this is what we call residual saturation for oil phase. And that's a very important parameter in data scale simulation. So in the pore scale, we can simulate this through Kahini and Navier-Stokes, assuming the two phase is fully immiscible. But there are many other cases. Fully immiscibility is not a good assumption. Well, it's common, we can say partial miscibility in many cases of petroleum engineering applications. In fact, the solubility on components, say, for example, consider a good example would be a gas and the oil two-phase system, gas and oil. So they are all consistent of hydrocarbon. And in the gas phase, and then many of them can lower the light components like methane, propane, and so on. But in the oil phase, it might be a heavy component like decane. So in this system, we see a substantial solubility of a gas component in the oil phase, and also a slight solubility of a heavy component in the vapor phase. And this solubility can affect many things like density, compressibility, surface tension, wettability. Consequently, they're going to affect the relative permeability and the capillary pressure function in the data scale. I want to just give you one example for the motivation. One of the benchmark example people doing in studying the oil recovery is the CO2 enhanced oil recovery. So normally when you find a new oil field, and the first thing you can do is drill a well, and you can get oil by just because the pressure is high in the reservoir, so oil will automatically flow out. And after a certain year, the pressure go down, and you have to inject something. So normally people initially inject water, then you get a water oil two-phase flow. And after a certain year, even water doesn't help because there's certain there's interfacial tension issues, and the people start to inject CO2. So CO2 can recover additional oil, and that's of the advanced techniques people doing. So at a data scale, people are studying why actually injection of CO2 can enhance the oil recovery. They find many major mechanisms. One reason is when you inject CO2 can dissolve heavily in the oil phase. That's caused the oil phase to swell. The oil phase swell. So because the oil phase swell, then the volume of the oil phase might increase by the residual oil saturation. So that can be washed out. And the second mechanism is that viscosity of oil phase might be reduced significantly because of dissolved CO2 component in oil phase, and that also causes the easy flooding or recovery of the oil phase from the reservoir. And additionally, oil component can also substantially dissolve in the vapor, what we call CO2 phase, but it's not actually vapor phase. It's quite heavy, but a different phase in the reservoir condition. So, but the CO2 phase have a much less viscosity compared to oil phase, so it's easy to follow. And also something the reduction in the surface tension can happen. So all of these 4 mechanisms actually is coming from the partial miscibility. If we want to study, say, the pore scale reason why CO2 can enhance the recovery of oil, we have to deal with partial miscibility. Otherwise, if you use an immiscible two-phase flow, you don't see any reason, then you say, then you don't understand why CO2 is better than water in terms of displacement of oil phase. So that's motivation. And there's many other cases, like if you inject methane, you can also enhance the oil recovery. If you inject nitrogen, you can also do so. All the gas injection is better than water, but the 3 gas injection scheme, they differ in efficiency. That's also because of the partial miscibility. So that's a main motivation for us to study partial miscibility. So recently we developed a diffuse interface model framework for multiphase flow involve multi-components that allow partial miscibility. So basically, the momentum equation is the same. The mass conservation law we can write for each component. The important thing is we are going to couple this with the equation with states, allowing us to model the miscibility. So this system is actually, looks simple, but it's very challenging to solve numerically because of strong nonlinearity and the coupling, particularly if there's a multiple components. So, so we now actually look at a few special cases of this framework to start with, and later on we're going to look at more complex cases. So I feel which phase? Diffuse interface is all modeled in this with this density. So, yeah, if, for example, in the methane, you have this mass density or molar density of this thing, and it can change greatly in the oil phase and the water phase or gas phase. It's okay. Either mass density or molar density can be. I'm sorry? No, that's a sharp interface model. We use diffuse, so we don't model that explicitly. So mathematically, the density is a continuous function of space, but have a sharp gradient across the interface. Yeah.
The interface is not, the layer is not too wide.
Yeah, that's also a thing. Yeah, so right now with this system, we have to, computational we only can do a small thing, like a 10 nano, or, yeah, it's small channel. We are talking about small channel anyway. Yeah, microfluids. Yes. Okay, so there's a few cases. Well, if for larger scale, then you can do mesh adaptation. Well, for 1D, probably is reasonable to do that. For multiple dimension, might be challenging. So one interesting case we can simplify the problem that still have engineering application is look at the equilibrium case. So equilibrium means suppose the velocity everywhere is 0, you have still some configuration you can compute that still have a meaningful physical thing you can interpolate. For this, we actually can use both formulation, like a Kahneman-like model and Elegant-like model to do this. So suppose both model, when you reach steady state, you give your equilibrium of the solution. And of course, this allows us to decouple, ignore the Navier-Stokes, and only concentrate on the phase field part of the problem. Also, Kahneman-like model sometimes also if the viscosity too large, and even though it's not equilibrium, but it's just velocity too low, you can still use this model to simulate the dynamic process well. So in the talk today, majorly actually talking about Kahneman-like model and Elegant-like model, how to solve this in terms of multiple component framework. But of course, we're also in ongoing work on coupling this with the Navier-Stokes as well. So when you reach a steady state, and the previous model is going to reduce to this one. So you can say that the chemical potential we actually define this way will be constant through the entire domain for each component J. And then we're going to show you how to define the equation of state later. So this is what we will solve, but numerically, to find the algorithm for this, we either solve electron and or kahinium such that we can get a sequence of solutions with time, and which are converging to the steady state we want. Okay, so one application of this is to find the equilibrium condition of the multi-component, multi-phase mixtures. This, in general, in the thermodynamics literature, is known as the flash calculations. I will quickly review of some of the flash calculations so that you can have understand what's going on. So this is an NVT flash calculation, and the NPT. Well, NPT is a standard, but NVT now is also getting popular. If you involve a bulk phase, that's actually in the textbook, but most likely just what we call zero dimension. You don't have a spatial distribution. So the input will be like an NPT. We're giving, say, the temperature, pressure, the amount of each species, and then we will compute the splitting of the phases for each component and other volumetric and solubility property. Similar NVT is that we giving temperature and volume instead of temperature and pressure, but we still also give the amount of each species to compute the other important splitting property. So, well, I'll skip this, but I just want to point out NVT now. In most of the books, if you find the flash calculation that based on NPT, but in most like 5 or 10 years, people also trying to say NVT actually is a better formulator, is more useful. So this is a formulation for NVT flash calculation that involving does not involve interface. So only for the two bulk phase. So basically, we have a Helmholtz free energy definition, which was already defined. And we're going to minimize this splitting such that this guy is minimized. And that is actually a statement of a second law of thermodynamics. And so this is just an optimization problem. And I'm going to show you, just you who want to use want to model hydrocarbon system, the Penn-Ramsey equation of state is what the most widely used. This have the following form. So that's going to define what is F here. So this F is just integration with this F with the space. Okay, by using, we solve NVT by using Alekan-like equations. So let me show you. The standard approach is just to solve the optimization problem, but now we can extend by using Alekan, allow us to do this extension of the flash calculating idea to multiple dimensions. So that's actually give us some information about the interface, and then we can predict, for example, the interfacial tensions. So I will skip some of the slides. What is the other method to predict the interfacial tensions? But the method we're using is a diffuse interface. Is one of the models that's more efficient than molecular simulation. But sharp interface model does not have a built-in mechanism to predict the interfacial tension. So the idea is like we have this F defined, and this FB is defined by equation of state, and this will be the gradient contribution for the interface, and we're going to minimize this. So and after minimize, then the Helmholtz free energy on the interface at the axis, actual energy will be the interfacial tensions. So this actually one consequence is this method allows to compute the interfacial tension. So we study this by using this minimization principle, and it can then once you find the solution, then you can compute the sigma with the interface. Like use the formula over here, and the numerical method is based on finite element to solve this Euler-Lagrange scheme. And after you get a solution, you can get a computed interface, interfacial tension like this. And of course, if you use a finite element method, then you can get certain bound on the error. So in fact, if you get this bound, is bound from one directions. And this is better than the most popular method people in the literature use, the finite difference method. You don't have this lower bound. You cannot bound from one directions. And then we can also use a mesh adaptation. Since it's just a one-dimension problem, it's not a big deal. And we use Newton method to solve a nonlinear equation, and then you can predict the interface. So for example, you can get interfacial tension as a function of the as a function of pressure, and this will be the distribution of the concentration for the two components. I think this is the two components. So this one is just 1D. So when we do in 2D, so this is a few years ago, we have a collaboration with Professor Zhonghua Qiao, and trying to extend it to multiple dimensions. We realize now in multiple dimensions, if you don't do a good to develop an unconditional stable algorithm, it's almost impossible to get the meaningful solution in practical time. Otherwise, the time step is too tiny. So what we did for a single component PR, we figured out a way to decouple, to split in the Penrose equation of states into an unconditional stable algorithm. And this is the main conclusion of this splitting. So it's actually has 3 contributions for Penrose equation of states. So we can treat ideal gas contribution repulsion implicitly, then we can treat the attraction contribution explicitly, so that you can have an unconditional stable algorithm to solve the transient problem from this multi-components two-phase system. And so I mean, give you one example. So without the gravity, we have so this is, I think, a single component, but you have two-phase, and eventually get the equilibrium, you have a special case. And the major thing I want to show you is that this convergence history for the energy is always decay in all the time, even in most recent time, always decay. So verify our results, and also compare with compare the experimental experimental data on interfacial tension with our computed one is very close. I think this some error here is from the parameter error, not the numerical error. So we can also compare the Yang-Plus equation from the finite method is almost the same. With gravity, then this thing we're going to go in down and eventually get a shape like this. And let me show you. So this energy also decay. We also make an effort to study the convex splitting treatment for multi-components, Penrose and fluids. But we have some result, but the result is not, I mean, the problem is not completely solved yet, since there's many complexity in that. It's not, so the result is we have some working solution, but it's not very clean, so we still work on this. So let me quick. So if you are interested, we can. I think I have one paper list here. I think over here. Due to time, I'm not going to. Oh, I don't think I put the paper over here. Anyway, so let me try and quickly talk about our most recent work on this convex splitting method. Is trying to do the compositional gradient simulations. So basically, if you have multiple component mixture, even for single phase, the composition is not homogeneous at equilibrium. Well, this can be counterintuitive. I mean, at the lab scale, because when we take a chemistry course in the high school, we define what's a single, what's a phase. A phase is just a homogeneous composition for the fluid, right? So at the lab scale, I mean, this is well recognized. But if you look at the geological scale, I mean, a kilometer scale, even for single phase, heavy component might go down and light component won't go up at equilibrium state. And this is also important because when you do a reservoir exploration, you need to know what's the initial condition. I mean, where this oil located. So even this could be served as the initial condition for reservoir simulation at data scale. So that is known as compositional gradient. Namely, we want to, if we drill well, if we can identify the composition at one location, we want to predict the composition in all the depths. Okay, so this at the data scale, what we do is we add the contribution of the Helmholtz fringe by gravity, and add it to the bulk phase. I mean, at the data scale, we don't attempt to resolve this interfacial energy, because that's too small compared to what the data scale kilometer omega. That is just a nanometer scale. We don't put this gradient contribution, but this allow us to track the variation with the composition as well as the splitting the phases. So if you have end up with two phases, the heavy phase will go down and light phase will show up. So again, the problem is trying to minimize the energy here. So this is a problem statement with gravity. Then we end up with, this is the equation we're trying to solve, Euler-Lagrange. But we add the time derivative, so the Alekan-like equation, so such as we can construct certain solution sequence. And we can first show that the Helmholtz fringe system defined by this equation actually decay, so the physically consistent with what we're expecting. Then in the literature, this actually is the first effort doing compositional gradient by using this Alekan type equation. Because in the past, people always just use many other things to either minimize this or to solve this directly. So this, to solve by this way, numerically, the good thing is it's very robust. We always can find a solution because this is always decaying. And but the time step is something we have to worry about because is requires sufficiently small if you do not use this unconditional stable algorithm. To design unconditional stable algorithm, we again apply convex splitting. So we have the scheme, and since I have time, I'll quickly skip that. It's a similar strategy. And let me show you a few examples. So the first example is the acid gas. So we have actually three components. So we predict this composition which components as a function of depth. So for example, so I think this first one is methane. So methane have is changing with depth, but of course the changing is not. It's still some change here. So it's from 22.6 and to 0.3, so it's not, you cannot ignore. And the other two is CO2 and H2S. And the second example is we use some published fluid mixture. People use to model the real fluid. And there's many components, but still use parametric equilibrium states. And the result is we're plotting this more scale, so you can still, so it's still single phase, gas phase. I think this, and you can see that the composition is changing. I think this is actually oil phase. So everything is in the oil phase. But the third example is everything is in gas phase, but there's so many components. And you can change. They also have substrate change. And the last example I want to show you is we have a few components here, but under certain condition you can have two phases exist in this system. So when you going down, and you can have a phase change from the gas to the liquid, and some parameter will have a certain discontinuity. But of course, the original PDEs can be still continuous by just numerically say a sharp gradient. All right. So in conclusion, we are looking at how to model two-phase multi-component system using Penn-Ramsey equation with states. And we find that there's a way to design unconditional stable algorithm by using semi-in-place time stepping, provided you use a good convex splitting. And in 1D case, we also did some adaptive finite element, but this could be extended to multiple dimensions as well. Some future work we're doing now is also trying to couple this with the nanosilks, such that we can study the effect of wettability and geometry on the behavior of the real fluid system inside the channel. And in the future work, we can also study a pore network model and also maybe the moving contact line problem for multi-component two-phase flow. So, and some acknowledgement with my collaborator and the funding agency. Well, thank you for your time. Which? Compositional, I mean, what's the title page?
The mass composition and equation of the DI model.
Okay. That's a word.
I'm curious about the momentum equation. Because for the diffuse interface model, we really act
yes.
Yeah, like a force in the momentum equation.
Yes. Now this one.
More than this one, like a capillary tensor.
Yeah, this is a capillary tensor, right? You have a cross product.
Yes, but it will include three elements, a potential.
Well, we didn't formulate in terms of energy here, but yeah, you can also equivalently formulate this term into a free energy. The free energy, yeah. That we can also write that. There's a few formulation for that.
For each component, you label with rho k.
Yes.
Usually we use the first term for the mass composition, right?
This is true.
Yeah.
And you also have a diffusion.
But for diffuse interface model, the mass conservation or mass continuity equation will only include the first term, first two terms.
For mass conservation, you only include the time derivative and the convection. You don't need this diffusion.
Since the third term we will add a similar term to the momentum equation, diffuse interface model. Your model is more like a continuous model?
Well, yeah, it's motivated by Kahneman model. In Kahneman model, some people also use this term.
So I'm confused because this is not like the classic.
Yeah, so what we're saying, if you don't want this term, you can add the contribute this term into the V, I think. That's something you can do. But for multi-component system, I think this term is more convenient to include the diffusion term here. If you have multiple components. If you have binary, you might able to remove this term but put the contribution here. Of course, for single components, you don't have this term. Single component, you don't have diffusion physically. I'm talking about the physical concept. Physical concept is you always have a diffusion whenever you have two or more components.
So the relation of the rho and the rho is rho cross summation of all the rho.
I'm sorry, I don't catch.
My question is the relation of rho and rho.
Rho and oh yes, right, yeah, yes, that's correct. Yes.
What about total energy?
Total energy of the system. That's the energy that incorporating for the bulk phase, and plus the gradients. If you have gravity, you have an additional gravity term. Then if you integrate this F through the entire domain, you get the Helmholtz free energy for the entire domain. That's the energy we track for this system, which is an NVT system. You have the volume and N fixed. You don't allow no flow boundary condition. P. Oh, this P. Well, this P, since it's compressible case, this P actually is consistent with the thermodynamic concept of pressure. So this P actually is the same P as we use. Yeah, we use here. Yeah, if you do an incompressible, you just take a limit, then the P loses meaning.
So that P could be resolved from the equation state. Yeah.
Correct. Yeah, that's another challenge to solve this equation system, because if the phase is slightly compressible, and to force this equation is kind of is very hard.
The total system
It's possibly compressible. We allow density is a function pressure. Yeah, for incompressible, you take a limit. Partial miscibility is a key concept. That's correct.
But how can you tell your simulation result from the general models from like the basement model to the incompressible conditions? Because I find phenomenologically like
How? You can, well, the major difference is Kahilian model, they use a very simplified equation for modeling Helmholtz free energy, double potential, which does not allow us to model solubility of a component to phases. And because of that, the whole equation is thermodynamically inconsistent. That causes a challenging numerical scheme. So from that sense, to design good algorithm for here actually, is slightly easier in terms of consistent for maintain the thermodynamic consistency.